Welcome back. We were discussing about the synchronization, and we have covered the frame synchronization, particularly the uniquot detection part of it in the burst, and then we just started on network synchronization, and in the network synchronization we talked about open loop synchronization, and then we were starting on the open loop synchronization in terms of time and frequency. So when you want to pre-correct, when the transmitters have to pre-correct, it should know that after how long time the burst has reached the receiver. So the actual transmit time at time t it has transmitted, that is the started the transmission, and the delay, that is the distance between transmitter and receiver divided by velocity of light, assuming that it's a constant propagation time. So with this he can estimate what is the time of arrival at the receiver. So the whole thing is depending on the delay, as well as of course the transmit time. Now similarly in the frequency domain, considering there is a Doppler, since the receiver might be moving or the transmitter might be moving, so omega 0 is the nominal transmission frequency and v is the relative velocity between the transmitter and receiver. In that case, the transmission frequency what should be corrected is pre-corrected is 1 plus minus v by c. The plus minus stands for the velocity is towards the transmitter or the away from the transmitter. V by c, that is the Doppler into omega naught. That is the, now these the time source or the frequency source, whatever it is, in fact time source is derived from the frequency source, these will have certain error, or your measurement might have some error. So therefore this pre-correction has to be corrected for the error also. So let us say the RE is the range, error range, the range in error estimate, error in the range estimate, error in the range estimate, and delta t is the difference between the time reference, that is the transmitter has a time reference, receiver has a time reference, they have a certain reference difference because their accuracy, stability, all these things are not same. Since they are not same physically, they are separate, so they may have a time mark, a time epoch at different, maybe at different time, transmitter and receiver. So that is the difference between time reference. So there is a time error Te is Re by c, that is range error by velocity, plus delta t. Delta t is the difference. Similarly, it can be done for the frequency. So v is the Doppler error, and delta omega is the difference between transmit and receive frequency reference. Each of the, as I said, that in case of time there is a frequency reference which may have some difference, and so the omega e, that is the frequency error, is the Doppler the v omega naught by c plus delta omega. The plus is it could be plus minus, I mean, depending on which direction it is going. Now the frequency references are specified by the there is a way of specifying by the maximum allowed frequency change per day with respect to the nominal frequency. So let us call it a small delta. Small delta is delta omega by omega naught, that is the allowable change of frequency with respect to nominal frequency, and it is change per day. So it is hertz per day. This is delta omega is hertz, omega naught is hertz, and per day. So it's specified as hertz per day. I mean, I am giving you some examples. Cesium is very stable oscillator. Cesium oscillator. GPS satellites uses cesium oscillator. Time references, they use cesium oscillator. So that is 10 to the power minus 12 to 10 to the minus 13. This is the order. Whereas our ordinary crystal oscillator is 10 to the minus 6 to 10 to the power minus 5 to 10 to the minus 6, depending on whether it's open control or ordinary. It may be slightly poorer than that. I mean, there is a range of the changes that is seen in frequency references. Now Now, if there is no intervention or correction, one thing should be noted, this offset of the nominal frequency will grow with time. So, if time grows, means the correction will be applied after some time, that after some time, as the time elapsed, this error or the offset will grow. So, this can be presented in a mathematical form, that is over time capital T delta omega and t is omega naught 0 to t delta dt. This delta is that frequency change per day, and over t it will grow, and the initial frequency, whatever initial frequency difference what was there. So, it is omega naught delta into capital T plus delta omega at 0, that is initial time when it started. So, this is the without intervention over the time capital T. Now, let us see the time scale. In the time when you do, actually time is counted with number of cycles from the same reference. So, cycle counting is the time reference, and so the cumulative time offset is related to cumulative phase error of the reference. So, the cumulative time offset over capital T time is delta omega t by omega naught dt, that is the phase error, plus the initial time offset whatever was there at 0 time when it started transmission, that time what is delta t. Now, if I replace that delta omega t from the previous equation, then it will become 0 to capital T delta t dt, delta omega 0 at 0 by omega 0 dt over again integrated over time t, and delta t 0. So, this gives us that delta into t square by 2, and because this small t is there, delta into t square by 2 delta omega 0 into t by omega 0 plus delta t at 0 position. So, this is the cumulative error. So, a designer or a operator has to know how long this will go on accumulating. So, how much error it can tolerate, after that he will apply the correction. So, that is how long he will wait for applying the correction, that is what is the delta t. So, based on the system error tolerance, this gives an estimate of when to intervene, that is what I said, when to intervene and apply a correction. Correction should not be applied very frequently, that is the cost of that. Now, that is about open loop synchronization. Let us go to a closed loop synchronization. Let us take a case of TDMA. TDMA is the best example for that. So, we will go a little more deeper into whatever earlier we have discussed about TDMA synchronization. Let us see. Now, it is based on the measured parameter of the transmitter, and then pre-correct the transmit time, pre-correct the signal time for transmitter. Now, it obviously is more accurate than open loop, because it is doing the real time measurement there itself. So, that if there is a drastic change, or if there is any change during the operation, which the open loop system assumes that this is a model, after some time it will do the either available data or model data he will use for pre-correction. Here it is more accurate. So, it will not allow the error to grow large. It is obviously adaptable to channel parameter changes during the communication, that is why it is more accurate, and but it is more complex, because you need a return channel, that means you need a receiver. So, it needs a return channel, and it needs a special signaling overhead, that we will see. And synchronization is synchronization time depends on the round trip delay. That is in case of satellite it is it's a 1/2 delay. So, that round trip delay is of the order of quarter of a second. So, that is also another constraint in that. Now, this TDMA satellite TDMA burst synchronization can be divided into two parts. One is the initial part, which is initial acquisition, another is the steady state synchronization. And from these two, we will discuss these two. From these two, we will try to see what is the synchronization accuracy and how do you select what is the guard time of that. Now, initial acquisition is a process to enter the assigned time slot at the satellite without interfering the other bursts which are already present within the time frame. You can imagine that, let us say there are 10 stations operating on a TDMA mode. Each of them has been given some specific time slots for transmission of their burst, and the station number 7 was not on, and it is joining the network. So, all 9 stations are working with their slots allotted and they are transmitting, and station number 9 is joining, station number 7 is joining. Okay. So, therefore, it has to enter the network such a way that it should not disturb the none of the other bursts, particularly the adjacent bursts. Number 6 and number 8 should not get disturbed. It should not overlap its transmission over their burst. So, that is the initial acquisition. And steady state synchronization is the once you acquire your slot properly, you know when to transmit, then the process used to maintain continuously the synchronization, the bus synchronization with the required accuracy is called steady state synchronization. And from these two we will try to derive what is synchronization accuracy and selection of the guard time. Now, let us say TDMA burst time plan, we will show you the plan. Let us nomenclatures, let us define with reference burst we will call B0, burst B, and 0 is the reference burst, followed by allotted burst. There are n number of stations, so Bn corresponding to bursts from a station n, where n is 1 to n. Okay. Since each a station has different range from the satellite, so it has different delay. So, it has to estimate the satellite range delay and transmits its burst based on the estimated start of the transmit frame, start of transmit frame, SOTF, I shortened it. We will see, we will come across this, but SOTF, you remember, start of transmit frame, which each station has to estimate. When a station starts to join a network, it should estimate its start of transmission correctly, so that it does not interfere with the burst from the other stations which are already operating in the network. This I have explained in terms of number 7 transmitting should not interfere with number 6 and 8, etc. This process of occupying its own allotted time slot correctly at the satellite is called initial acquisition. It is very clear. Now, let us see pictorially. Let us say this is the frame F. You can call it in terms of bits or in terms of time. The frame number k is starts from here, and next frame, that is k plus 1 frame, starts from here. So, first is the reference burst. So, B0 is at the beginning of the frame, and it repeats after the f bits or f time, and the allotted bursts are for station number 1 B1, which is from T0 it is away. So, it is given a time T1. Similarly, this should be B2 is allotted time T2. It could be another reference burst also, as we have discussed during our TDMA discussion, that there could be single point failure. So, there will be at least 2 reference stations. So, that is why it could be B0 also, but let us take that this is mistake and we take it as B2, and the nth is Bn. There are capital N number, so last one is B capital N. So, the start times are T1, T0, T1, T2 with respect to T0, T1, T2, T2, Tn. So, F is the frame time, Tn is the station n burst start time with respect to start of transmit frame, is start of transmit frame, Bn is the burst of a station n. So, the station 1 whose position in the time frame is B1, he has to estimate is this is if he is he himself is the reference burst. So, he should have transmitted start of transmission transmit frame, he should have transmitted at some point from there, which is T0, from there T1 time away he will transmit his burst. So, he will reach. Similarly, station 2 or station n will estimate SOTF n for his position and nth position with respect to that nth position delay. So, as if he is replicating what is happening at the satellite, that is with respect to reference, but the point is he is imagining as if he is transmitting the reference burst. How he will know that when is SOTF should be there, that is the question. So, this diagram and related some discussion we had held earlier, I will repeat that, that is at the satellite same way of presented, that is reference burst is shown in color here f and is repeating, B0 is here, Bn is here, and let us say station n, he receives the reference burst which is called start of reference frame. So, he receives the burst and he transmits at this position with respect to start of transmit frame. Now, this is imaginary, he does not know. So, this delay he calls capital D. He has measured this start of reference frame, and if he knows this D, then after t n time he transmits his burst, it will reach the correct position, and he can verify, he will receive that reference burst which is received like this here, and the delay t n he will receive at the t n. So, he will know the correctly he has transmitted, but the point is how he will know this D which is not known to him, how he will estimate. Now, this can be estimated very simply. In pictorial you can see that when it is happening at the satellite, here the reference burst B0, and after m frames, m into f, f is a frame time or frame number of bits, whatever way you can calculate. So, after m frame this whole thing is happening. Now, at the same time at the receive station or this this particular station, it is a start of reference frame comes after a propagation delay, and when he transmits is imagining he is transmitting the reference burst. So, after a propagation delay it will reach the satellite. So, this is 2 times the propagation delay of the nth station, Pn is nth station propagation delay to the satellite, and plus d. So, 2 times Pn plus d gives you Mf. So, it is a simple equation, d is Mf minus 2 times Pn. M is a integer number which is integer number of frame has passed. Normally these frame durations are very small, of the order of 4 millisecond, 2 milliseconds, whereas propagation delay is 125 milliseconds. So, therefore, it is same time f, and then the f is the frame time, Pn is the propagation delay between the satellite and the station n. So, you have to select this integer m such that d is less than f. With this condition you can easily find out. So, burst transmit time with respect to the reception of reference burst will be d plus Tn, d plus the allotted slot time Tn. So, this up to this we have seen earlier, but while initial acquisition he actually has to be more careful of transmitting exactly here, because just a guard time away the other burst is waiting. So, if your propagation delay calculation is wrong, you will fall into that. So, therefore, he should not transmit at the beginning of the burst, he should transmit somewhere in the middle of the burst with a very small pattern. That is what is initial acquisition. So, initial acquisition, the station n identifies SORF by detecting the reference burst uniqueward. Then it transmits a small few bits which is preamble burst, that PB the nth station. So, PBN, which consists of the carrier and bit timing recovery and the uniqueward, because this demodulator has to detect that particular burst. So, CRBTR is necessary and uniqueward is frame synchronization. So, this preamble he transmits. So, it is much smaller than that capital N, that is burst time, so at the estimated center of the allocated burst position. So, therefore, the transmission is Tn delayed, that center of the burst position is Bn by 2 and the preamble by 2, subtract the preamble by 2. So, then you get the start of the preamble, but the whole preamble will sit at the center of the burst. So, the transmit time with respect to SORF will be Mf minus 2 Pn, that is your D, plus the Tn, plus you are moving to the center. So, Bn minus Pbn by 2. So, that is how it is to be calculated and transmitted. So, center of the burst is targeted. So, that estimated error should not create, if there is a estimation error, should not create interference to the adjacent burst. And accuracy depends on the twice of the range prediction uncertainty, that 2 Pn. So, whatever prediction you have done, that uncertainty or the propagation delay estimation. So, there is some estimation or information available based on that, whatever error is there. This is shown in pictorially like this. A burst consists of Pbn and the rest of the things are data. So, this whole thing is Bn. Now, this is B0 and the Bn has to start after Tn, it should start here, the dotted line. The center position, this Bn by 2 is here, that Pbn is the preamble of the nth station. So, Pbn is placed exactly at the center. So, that is why start of Pbn will be Bn minus Pbn by 2. That is where you should start transmission. So, that is at the satellite time, right. Now, the received preamble burst time with respect to the received reference burst time of the same frame is then compared with that. That is the that, as I said, at the you transmit and then receive and you find this difference of time. Okay, is then compared with the allotted time. The time correction is then applied in subsequent, if there is a error, then time correction is applied in the subsequent transmissions. A full burst transmission with the actual data from the allotted burst location starts once the correct burst center position transmission is achieved, but it can be achieved very fast. Assuming no uncertainty, initial acquisition can be done in 2 hop time. You know where the acquisition is. So, that is about the initial acquisition. Now, how of the steady state synchronization? Due to satellite range drift, the transmitted burst may reach satellite early or late than the allotted time with respect to the reference burst, because this is when you have acquired. After that also satellite is drifting. So, you have acquired and you have fixed the clocks such that it will transmit exactly at that your based on your calculation of the d. But then satellite itself is drifting. So, there will be more delays, either more or less delays. So, there has to be continuous synchronization has to be required, that is steady state synchronization. So, for that the shifted burst and the reference burst appears in the local receiver, what is coming down from the satellite, and that has to be compared with a locally generated burst with respect to the received burst reference as per the allocation. This the difference between the locally generated ideal burst start time and the actual burst start time shows the phase and amplitude of the time error what happens. So, pictorially it can be shown like this, that is the I repeat for your reference, that is difference between the locally generated ideal burst start time and the actual received burst start time shows the phase and amplitude of the time error. So, you receive the B0 and you receive the Bn, which might have shifted. This is the allotted time, but because the satellite has drifted, so Bn has reached here a little actual Tn is actually, and what satellite has received it will retransmit down. So, you will receive it slightly away. Now, locally you can generate with respect to the Bn at after Tn, which is the allotted time, you generate a local reference. This is supposed to come, whereas you have got this. So, there is a time error. So, locally generated burst time and the received burst time beginning will give you the time error. So, this time error has to be corrected every frame slowly. Now, let us see the accuracy part of it. Before that, let us try to understand what is the error. So, maximum propagation time delay to a satellite P is the range by C. C is the velocity of light, R is the maximum range. So, the maximum correction rate is 1 by 2 P, because after one hop you are able to correct. So, it is C by 2 R, that is corrections per second. That is the correction rate, so many corrections per second. Now, what is the worst case synchronization error between two consecutive corrections? between two consecutive corrections, what is the synchronization error? That is E is equal to dr dt by C and 1 by f max. F max we know, C by 2r. So, that makes E is equal to 2r by C square into dr dt in seconds. Okay. So, that is the total error. Now, synchronization accuracy and guard time, you have to design the guard time accuracy. Overall accuracy determines the guard time between the bursts, between two adjacent bursts during normal operation. It depends on the accuracy and stability of the frequency source. One is the accuracy and the stability of the frequency source, and then basic resolution of the clock or the timing operation. Resolution of the clock also comes into picture, and then range and range rate of the system, maximum of that, and then the circuit jitter, clock jitter. If there is a switching time delay variation at which the logic is different, these are very high speed logics. So, all these contributes to the error, and error can be positive or negative with respect to the reference burst. So, the error burst x and x1 between these two bursts could be in opposite direction. So, the guard time should be 2 times, guard time between two bursts should be twice the synchronization accuracy. So, considering all errors, it becomes GT is 2 times 2E basic resolution, clock drift, clock jitter all together. Now, this last 3 points are small, highly stable oscillator. So, therefore, GT is 2 times 2E, that is 4E, which is 8R by C square into dr dt seconds. So, with this what we have covered is frame synchronization and Unicode detection techniques, open loop network synchronization, estimation of the time drift and the frequency drift, and the open loop. Closed loop network synchronization, we have taken a TDMA example in that initial acquisition, steady state synchronization, and the accuracy and guard time selection we have covered. Thank you very much.